Okay, so I'm going to start the revision day school. As I remember, we could not finish the unit two. I think I did only three sessions, and I think final exam is scheduled on May 27th, right? Are you aware of
Yes,
that?
sir. Yes, sir.
Yeah. So today I'm going to focus on the unit one, which I did stereochemistry, and then within next maybe week or two, I will finish the remaining three sessions of the unit two. Then I will do a problem discussion from unit two separately after this. So today we'll be focusing only on the stereochemistry. Okay, right. So I will discuss some past paper questions. Questions from past papers. So this is So there's a similar question last year as well. So I don't have it here, but very similar to this. But this one has more parts than the last one, last year's question. Right. So this is from 2022, 2023 final exam, stereochemistry. So you will be getting four questions, right? Like the same format like last time. Uh, One question from stereochemistry, you have four units, one question from each. Okay. Uh, okay, so let's look at this. So it says the given below is the structure of compound A, and so carbon atoms are already labeled for you. And okay, and so in this kind of questions, you don't have to worry about labeling carbons according to the nomenclature. This is nomenclature. This is just to identify the carbon atoms, just to do the stereochemistry problem. So, in the question, it's already labeled, so then you don't have to worry. Uh, Now, since this is a revision day school, you need to, give answers. You need to speak, okay? And also, like I always tell you, like if you don't have questions, if you got nothing to say, please keep yourself muted. Otherwise, it'll be really disturbing. If someone's mic is on. Okay. So first it says calculate the number of stereoisomers possible for A, draw the structure of the enantiomer of A and label it as B, draw the structure of the epimer of B and label it as C, and so on. Okay, so I'm not gonna. So we'll take these questions separately. There are like five parts to this question number one. Okay, so the first part, calculate the number of stereoisomers possible for A. So how do you do that? Like first, what is the first step? First step we need to do. How do you approach this question?
Calculate how many stereo centers are there.
Yeah, you count.
Count. Yeah.
Yeah. So how many stereo centers are there or stereogenic centers?
Three.
How many?
Three.
Yes. So we have this double bond could have two stereo. What is it? Okay. So the the double bond can have two isomers E and Z. So therefore, this is considered as one stereo center, and this is the other one, and this is the third one. So you have three stereo centers or stereogenic centers. So, So I'm going to tell you for the last time. So if you don't have a question, if you got nothing to say, please keep yourself muted. Otherwise, you're disturbing the whole class. So if you're making too much, unnecessary noise, I'm going to remove you. Okay. Right. So then they're asking, calculate the number of stereo isomers possible for A. So how many isomers possible then?
8.
Yes. So it's very simple, straightforward. So you show that there. I don't know why you guys don't understand. Why can't you keep this muted? I mean, if you got nothing else to say. Whatever. Right. Number of stereo centers or stereogenic centers, 3. Then we know that to calculate the number of stereoisomers, you take 2 to the power n. N is the number of stereo centers. And so then it'll be 8. So that's the answer. It's very easy, straightforward. You just count the number of stereo centers. Then, yes, Hansi. Do you have a question?
No, sorry, sir.
Okay. Right. Then the next part is to draw the structure of the enantiomer of the A and label it as P. So enantiomer is the mirror image of this molecule. We know that that's the enantiomers are mirror images, and the other important thing about that is they are non-superimposable mirror images. And I think I explained to you when we talked about this. They're not. They're two different molecules, but they happen. Their connection is their enantiomers, or their relationship is they are mirror images of each other, non-superimposable mirror images. Okay. So it's not that we take the mirror image, we draw the mirror image of this. Okay. There are two molecules and they have the same connectivity, same molecular formula and everything, but their spatial arrangement is different and they're connected. Their relationship is they are mirror images of each other or they're enantiomers. And these mirror images are non-superimposable. So it's simply you invert this the way you draw this enantiomer of A is to invert the stereo centers. This one. I don't know. Only you guys have this issue. Why can't you keep this? Hello, who is this? Yeah, I'm not going to continue this class. This is really crazy. I don't know why you guys ඔයගොල්ලෝ තේරෙන්නේ නැද්ද ළමයි මේක මියුට් කරන් ඉන්න ඕන කියන එක දැන් එක එක සද්ද එනවා කියන තේරෙන්නේ නැද්ද ඔයගොල්ලන්ට ඔන් කරාම right. පාඩම කරන්න බෑ මේක අන්මියුට් කරගෙන දඟලන අයියෝ මම අන්තිම පාර දැන් try කරන ඔයගලන් ආපහු සර සද්ද කරොත් මම හැම lecture එක නවත්තලා නිකන් ඉන්නවා. Okay, so what I was saying, so to get the enantiomer, so you just invert the stereochemistry of each stereocenter here. So the enantiomerism occurs only in the tetrahedral around the tetrahedral carbon atoms. To get enantiomers, what is the requirement? You need to have four different groups around the carbon atom. So then we have such two such stereogenic centers or stereocenters. So you pretty much invert the stereochemistry when you draw the enantiomer. So this the bromine in A, it's coming towards you, and you draw it like in the B, in the enantiomer or the mirror image. You draw it so that it is going away from you. So in A, OH is going away from you, and then in the enantiomer it should be other way around, or it should be inverted. It should be drawn like it's coming towards you. So that's, this is the answer, and that's the compound B, or the enantiomer of A. Okay, then part 3. So they're asking for epimers. Draw the structure of an epimer of B and label it as C. So just to give an idea, so we have discussed this during the day school. If you don't remember, you should go back to your reads and to notes. And who's this 4, 2, 3, 5, 4, 5, 6, 7, 5, 6, 7, 4? 4, 2, 3, 5, 4, 5, 6, 7, 4. Hello? Okay, can you guys still hear me?
Yes, sir.
Yes, sir.
Okay. Right. So the epimers are when you have, there are molecules, chemicals with more than one stereocenters, or, several stereocenters. So when there's only one stereocenter changing, so only one chiral center is changing between the two compounds, then their relationship is epimers. Like this example I have given here, D-glucose and D-galactose. See, like all the ones are same, okay? But only this is inverted. So this is inverted, so only one chiral center with different configurations. So they are called epimers. Their relationship is epimers. So they can't be enantiomers or anything, because they're not the mirror images. So then there's only one stereocenter is different, or they have different configuration at one stereocenter. Then these are the connection between them, or the relationship between them. They are epimers. And then they're asking for the draw the structure of an epimer. So the B is the enantiomer of A. Okay, so the original molecule was A. That was the molecule given in the question, and you drew the enantiomer of A, that is B, and they're asking for epimer of B. So then don't get confused, these kind of questions. Don't draw the epimer of A, but you need to draw the epimer of B. So you can draw, there could be, two epimers, because there are two stereogenic centers, so you can change either one of them. So therefore you can change, so this one is C4 epimer, where you change only the C4 stereo center, like you invert the bromine and you get this one, C4 epimer of B. Or you can keep the C4 intact without changing C4. You could change C5 and make it, you invert the hydroxyl group. So this is coming towards you. Now it's going away from you. And so you kind of change the stereochemistry. So when you compare B and B and C, these two, they are the epimers, and these also epimers, because there's only one stereocenter is changing. So if they're enantiomers, all the stereocenters should be changing, should be inverted, because they are mirror images. But epimers, there's only one stereocenter. The configuration of only one stereocenter changes. So that is the meaning, the definition of epimers. Right. So then the last question is the last part, I think, of the same question. It says the compound D, compound D, which is an isomer of A. Again, it is an isomer of A. Okay. So remember, all these enantiomers, epimers, all these are isomers. So all of these different stereoisomers, different types we talked about, they're all isomers. So it says which is an isomer of A. So compound D is an isomer of A and gives the same ketone as A on oxidation with PCC. And they're asking you to draw the structure of D. So see, again, I have put the structure of D here. So, sorry, A. So this is the original structure given in the question. And they're asking you to draw the D, which is an isomer of A. And when you subject D to oxidation with PCC, it will give you the same ketone as A. So that's the question. So first, let's look at what PCC is. Pyridinium chlorochromate is an oxidizing agent, and so when you have alcohols, okay, primary alcohols are oxidized to aldehydes using PCC, and this is the mechanism. So we're not gonna go through the whole mechanism, but I just included this so that you know what PCC does. So it oxidizes primary alcohols to aldehyde. So then so here the example is only for primary alcohols, but it does oxidize the secondary ones as well and give you ketones. So in the question, it says the D, which is an isomer of A, will undergo the oxidation with PCC to give you same ketone. That means either you take A or the isomer of A. It's the isomer of A. Both will give you same ketone. That's what they say, right? So what they are asking for is the D. D is the question. So by draw A, see, remember, like A is, yeah, I'll draw A again in a bromine. Sorry. Okay, so this is this was A, and if you react this with PCC, what do you get? Say bromine and your ketone, right? So this is A, and they're saying you would from D also you would get the same ketone. So then D is an isomer of A. So what is the D then? So then what is D now? Can somebody tell me the answer?
Diacetyl.
What is it?
මේ OH minus වල ස්ටීරියෝ කෙමිස්ට්‍රි වෙජ් ලයින් එකක් තියෙන.
Yes, because you see now to get the same ketone, you cannot change the bromine. So you can't change the bromine, and the PCC won't react there. PCC will only react here. PCC will react only with the hydroxyl carbon. And to get the same ketone, so D has to be an isomer of A, and then if it is to be an isomer, only thing you can do is you can change the stereochemistry here. And so the D should be bromine and phenyl ring, and like this. So it's now the OH is coming towards you. So that's the structure of D should be, because both with the irrespective of the stereochemistry at this carbon, carbon 5, so you could get the same ketone, because when you make the oxidation, when you do the oxidation, so that stereocenter is gone. So it's now sp2 carbon, and it has different stereochemistry. I mean, it can still be enantiomeric, but it's different. So therefore the D should be this one. Okay, so for this, I mean, you don't need to know the mechanism of PCC reaction, but at least you should know what PCC does. It does the oxidation of primary, secondary alcohols into aldehydes and ketones. And then to get the same ketone, that means you're changing only the stereochemistry around the hydroxyl group. Okay, that's the question number 1, part 4. And the part 5, we have done this many times, many examples during the day schools. It says, according to Kahn-Ingold-Prelog rules, label the groups in priority order and determine the configurations of stereocenters as E and Z or R and S. Because we know that there are 3 stereocenters. The first one will have E or Z, and these 2 can be labeled as R and S. So then for the let's start with the double bond. So you have methyl group, hydrogen, and a carbon attached to bromine. So then again, we use the same priority rules, according to the atomic numbers. And in double bonds, when you have alkenes, what we do is, we kind of divide the molecule in half like this, not really, but then you try to prioritize the 2 groups on one side and the other side. So when you compare the CH3 and hydrogen, definitely hydrogen has the least priority, and CH3 has the most priority among those 2 groups. Therefore, CH3 becomes 1, hydrogen is 2, and here the first atom is hydrogen, and this one is carbon, and it's attached to bromine as well. So therefore, this gets number 1, and the hydrogen is number 2. And then so now you can see the least priority groups are kind of diagonal from each other, and also the highest priority groups also diagonal. And so what is the configuration when you have that scenario? Is it E or Z?
E.
Yeah, it is E. Okay. Right. So that's done. Then we go to the next one, carbon number 4. And you have, so when you, okay, remember this, when you try to find out the RNS, make sure that you draw all 4 different groups around that carbon, including the least priority group, which is hydrogen. Since bromine is coming towards you and in a tetrahedral setting, so we know that 1, 2, 3, 4 groups. See, like if one is coming towards you and the other one is going away from you, and then there will be 2 bonds on the plane, right? So 2 bonds on the plane. So we already have 2 bonds on the plane. These bonds are on the plane. Let me redraw this so that it'll be clear. See, these bonds are already on the plane, right? And the bromine is coming towards you. Therefore, the hydrogen, the 4th atom attached to this carbon number 4, hydrogen should be going away from you. So then this is it. Then you label them according to the priority. So bromine gets number 1. And how do you pick the number 2 and number 3? So see, now both the atoms are carbon. So here also carbon, here also carbon. Then when the atoms, the first atoms are equal, we go to the next atom. And here the next atom also carbon, but it is like, since you have a double bond, it's like attached to 2 carbons, but it doesn't really matter because this carbon attached to oxygen. So therefore it gets higher priority. Therefore this carbon, it will be number 2, and this is number 3, and hydrogen is number 4. Now, then how do you read the R or whether this is R or S? So you hold the least priority group away from you. Then you kind of, it's like when you hold the least priority group away from you, so you will see other 3 groups. See, the least priority group is in the back, which is number 4. Then you consider the priority of the other 3 groups which are looking at you, like at the base of a cone. Okay. So now 4 is away from you. And so the bromine is 1 and 2, 3. So that is S, right? Is it correct?
Yes.
Right. So then we go to the next one. So this is done. So you go to the next one, number 3. And now you have hydrogen is coming towards you. And the hydroxyl gets the number 1. And number 2 is this carbon because it's attached to bromine. And this is number 3. And hydrogen is coming towards you. You can do 2 ways. You can read the priority as this is, because now you can, hydrogen is coming towards you, but ideally we have to hold it away from us. But you can figure out the stereochemistry as it is. Now if you see, it's actually like again like S, but since hydrogen is coming towards you, you have to invert that. So then this is actually R. Okay, let's see the answers. So this is 2E, 4S. This 2E means, just the carbon number, okay? 4S is the carbon 4. Here it was the carbon 4, and 5R. So did you understand the third one? Anybody who did not understand the third one?
Yes, sir.
Yeah. Or if you want, you can redraw this, or you can try to imagine this in your head, like if you're holding hydrogen in your hand, like it's the way you have to imagine is you take the least priority group in your hand, like you hold it and you hold it away from you, and then you look at the other 3 groups, at the bottom of a cone or a pyramid, something like that. So then you can imagine, like, you're holding the hydrogen away from you, then see whether you can imagine the other 3. So then you can figure out the stereochemistry. But I think this is less confusing. If the least priority group is coming towards you, you figure out the stereochemistry as you see it, then you invert that. So that's simple. Okay, that's how you get.
Excuse me, sir.
Yeah.
Is the carbon number is important? That 2E, 4S, and 5R?
It's not really, because I mean, it's better if you can put that there, because the compound is already labeled for you, so that for clarity, then we know what carbon center you're talking about. Or you can, I mean, if it is really confusing, you can put a arrow. Okay, this is R, and you can put something like that, because we just need to identify which carbon you're talking about. Okay.
Okay, sir. Thank you.
Right. The part B of the same question. Consider the following cyclohexane labeled as E. So there is a cyclohexane given. So we had a separate session on cyclohexanes. And so I hope you remember the material. And okay. And so the question is asking, draw the two chair conformations of E. So we learned about the cyclohexanes. They exist as mainly as two chair conformations, but there's another one called board conformation, but it's very unstable. You don't have considerable amount of board conformation, but therefore we just consider the chair conformations, and you have to draw the two chair conformations of E. Then the part 2 is giving reasons, identify the most stable chair conformation. Right. First of all, before we solve this, before we give the answers to these questions, let me show you how to draw these chair conformations easily. Because what I have seen, students, they struggle to draw these chair conformations. So if we cannot draw them correctly, then you can't answer these questions. You cannot get the answer, because there's axial and equatorial positions, and to show the stereochemistry, see this is coming up, this is coming up, and this is going down. Then you need to be able to draw the chair conformations correctly, so that you can depict or show this stereochemistry accurately. So there are only two chair conformations for one cyclohexane. So let's take this 1 and 2. Okay, I'll show you how to draw the 2. See, first you would draw two parallel lines, and just look at the screen and try to absorb and put it in your head and practice. Okay, so you do draw two parallel lines, and they're not totally aligned. One is you just slide it to the right, and so then you draw another line, another two lines, like blue lines as shown here. Okay, then you just join them. That's the third step. So draw two lines like this, and okay, it's hard to draw using my notepad, but so you draw this, that, then you combine the edges. So the other one is toward it's like the mirror image of the first one. So you drew two lines like that. Then you do the same, and you combine it. If you have a pen and a piece of paper, can you try now? Did you understand? Is it clear?
Yes, sir. Yes, sir.
Yeah, you can try on your own, and then you won't go wrong with drawing these conformations of cyclohexane. So all you need is two parallel lines. So if you draw one, then you have to do the kind of mirror image to the other one. So it's easy. So let's draw together. I mean, if you have a pen and a paper, so 2 lines, then make it a V, an upside down V, then join. And the other one, 2 parallel lines, make it a V, okay, upside down V, then join them. Isn't it easy?
Yes, sir.
Okay, so now you know. Then I will upload the recording, so then you can see the recording, and then you can try drawing this, because you should be able to draw the cyclohexanes properly. Right, the answer. So okay, so this was the question. So we had okay, let me go back. Yeah, CH2, CH3, CH2, CH3, CH3 and bromine. Okay. Right, so then you should know, like, practice to draw the hydrogens. I mean, you don't need to draw hydrogen, but the axial and equatorial positions, these have, these are axial positions, then the axial, equatorial, axial, equatorial, equatorial. So you should be able to draw so each side, just imagine, this cyclohexane is not a flat molecule, but these, if you can draw like in the middle to dissect the cycle, like which is perpendicular to the cyclohexane ring, then you can see, these 3 atoms will be, I'm talking about this kind of plane, okay? Like a horizontal plane dividing the cyclohexane. So then you have a top and bottom part, and this, top 3, these atoms, there are 3, and there's another 3 at the bottom as well. So, okay, I think I made a mistake. See, this one has, there'll be 3 axial on top and also 3 axial on the bottom. Understand? So make sure that you practice to draw these axial and equatorial positions. Okay, so now, so first assume that we have drawn the 2 conformations, and then you have to show, so what was the first, draw the 2 chair conformations of E. So then if you don't have any substituents, I mean, this is all you have to draw. You only draw these 2 just for the cyclohexane, but this is a tri-substituted cyclohexane. There are 3 substituents, and then you have to show the stereochemistry correctly. And so the CH2, CH3 is coming up, and CH3 also coming up, and bromine is going down. So that means you have to select, see here you have axial, and here you have equatorial, axial, axial, equatorial, equatorial, axial, then axial, equatorial, equatorial, axial. So you have to pick the correct, whether it's equatorial or axial. See now, and the other thing is the positions, 1, 2, 3, 4, 5, 6. So this is 1, 2, then the 3rd position and the 4th position. That's where you have your substituents at. So then, so it says CH2, CH3 coming toward, coming up, coming towards you, star. But in this carbon number 1, you can say only the equatorial bond is coming up. Axial bond is going down. So therefore, you have to pick the equatorial bond to attach the CH2, CH3. So that means when you look from above, when you look from above, this is coming towards you. Okay, so this is where if you look from above, then the third carbon, at the third carbon, there's a CH3 substituent that's also coming towards you. And also here, the equatorial bond is coming up. So then you choose the equatorial bond. You leave the axial one because axial one is going down. So if CH3 had a wedged line, like the other stereochemistry, if it is inverted, then you would have used the axial bond. It should be, since it's going down. But here it's coming up. Then the bromine is going down, right? It's a dashed line, dashed wedge. So then to show the bromine going down, so here we have axial and the equatorial. The equatorial bond is going down. So then you put bromine as the bromine with the equatorial bond, so that we can show it's going down. And the other one, the other chair conformation, we'll have to have the same stereochemistry, okay? Only the skeleton changes. And we know when you flip the ring, during the equilibrium, when you flip the ring, equatorial become axial and axial become equatorial, right? So that's what happens when you flip the ring during this during the equilibrium of this chair conformations. Now, I mean, as I said, you should, the other conformation also should have the same stereochemistry. Now, in the other ring or the other conformation, so bromine should still going down, but now it is it's in the axial position. See, now the equatorial position is coming up, and see, it's all changed. I hope you understand what I'm saying. And so therefore now bromine is in the axial position, and the CH3 should be still coming up. Now it was before equatorial, now it is axial, it's coming up. And CH2, CH2 also axial, it was equatorial before, now it is axial, it's still coming up. So do you understand that, how to put the substituents there? You okay?
Yes, sir.
Hello, sir.
Yes.
Hello. Can I talk to you?
Yeah, sure. Go ahead.
Sir, I was in a crowded bus, so at that time my mic was unmute. So then you were removed me by that one. So can you give me the permission again? I joined from another phone, but I have to leave the place now. That's why.
Yeah, because it's so much, too much disturbance. I've been having this problem with you guys. I don't know, like, why you can't keep it mute. So I don't see you. You're trying to join the meeting.
I tried several times, sir, but I couldn't connect. You removed me, so
Now you joined, right?
No, this is not my phone. I went to the library and asked from a student studying there and asked her phone to send you the message. Not my one.
Yeah, I don't know. So I can't see that you're trying to join. So maybe you can try to join again. Then I can try to accept it. If not, I will upload the recording. I'm going to upload the recording. I'm not sure why I don't see you. Like, I didn't see any.
Now I am trying to rejoin, sir, but I get message you are unable to rejoin this meeting because you were previously removed by the host.
Yeah, so I don't know what to do. So can you so there's a classroom at CRC where you can join the same meeting.
Sir, I'm in Horana, sir. That's the matter, and I had a half day leave for this one and came. That's why.
Yeah, I don't know what to do. So then, because I don't know why the Zoom is not showing you again, and I don't know how to add you.
Then upload the recording, sir. Then.
Yeah, I will. So I'm recording this. So then, I mean, it shouldn't matter, right? So you can. Because the reason I'm removing you guys, because I told you in English, Sinhala, I don't know how to say that in Tamil, otherwise I would have said that. And it's really disturbing. There were like, I don't know how many people. too many people did the same thing. So then I was only left with removing you, if you're disturbing us. I'm really sorry. So I didn't have any other choice.
Okay,
Okay.
sir, sorry, because crowded people came to my phone and suddenly it happened. That's why.
Okay. Right. Okay. Okay. So any other questions? So did you understand, like, okay, now we did how to draw the confirmation and then how to put the groups on the ring? And did you understand that process? You okay with that now?
Excuse me, sir.
Yes.
So when we number the carbons in the ring,
Yes.
should we can we number as we wish, or
Yes.
we follow the normal?
Here you don't have to worry about that. I told you it's not about the nomenclature. It's just about identifying, where they are, just their relative positions. Because see, like, so you have, let's say, if you have CH2, CH3 on the first carbon, then there's a carbon without substituents, then the third one, the fourth one. Just to identify the relative positions, you can label them as you wish. If in the question, if it is already labeled, continue that labeling. Otherwise, you can label them as you wish, or you don't have to label them. I mean, there's no point. I mean, there's no need. But I just put the number so that it's easy for us to get the relative position. Otherwise, you could because just looking at the flat ring is different, and when you draw the cyclohexane, the confirmation, you might miss the positions because it looks different. Okay.
Okay, sir. So in the chair confirmation, so always the carbon we number as the clockwise.
What do you mean? No.
Right.
I just put it that way. I mean, you can put it other way around as well. It's as I said, it's just to know the relative positions. That's all. Okay.
Okay, sir. Thank you.
Right. So then the next question was to figure out which is the stable conformation. So definitely this is the stable conformation, because we learned that when you have bigger groups in these 1, 2, and 3. See, again, it's now no need of proper numbering, just the relative positions. We know that when you have 2 substituents on attached to the first carbon and the third carbon, so then we have something called 1,3 diaxial interactions. So okay, so 1,3 diaxial interaction. So that will make the conformation unstable because of the steric interaction, steric clash. So you would draw these axial groups and show that they are interacting with these arrows that kind of indicate they're having steric clash, they're in their way. So therefore, conformation 2 is less stable. Conformation 1 is more stable, because these bigger groups, they are in the equatorial positions, they are kind of away from each other, so there's no steric clash. And therefore, so you can mention there's no 1,3 diaxial interactions, but the number 2 conformation has 1,3 diaxial interaction. So therefore, it is unstable. So that is the answer for the next part 2 of the question of the same question. Right. So that's the end of that question. And so the next question is on the optical rotation. So we learned that during the day school, what is the optical rotation, specific rotation, and everything. Just to remind you, what is this optical rotation is, we know that when these chiral molecules, or these enantiomers, or the molecules with stereocenters, chiral molecules, when they are subjected to plane polarized light, they tend to interact with this plane polarized light and rotate the light in, it could be clockwise or anti-clockwise direction. And I think I mentioned this specifically. So this the clockwise rotation is called the clockwise rotation. If the light gets rotated in the clockwise direction, it's called plus. Anti-clockwise minus. And this is not related to the ROS. This R and S system is something invented by people. Like we devised that system so that we can identify the two enantiomers. One is R and the other one is S. So it is not a property of the molecule, but this the rotation of the plane polarized light is actually it's an inherent, like a intrinsic property of the molecule. So the molecule can rotate. So molecules actually it's their own property. They rotate the molecule by interacting with the incoming light. So therefore the this light rotation and the RNS, there's no interaction, there's no connection. Just to remind you that. And so usually we do that. So this is too much details, but okay. That's just to remind you.
Excuse me, sir.
Yes.
So I have a small doubt. So you said that
Yes.
that X are rotated in L and D are not related to R and S. So, but I remember learning something like if one of, like, let's say R enantiomer of molecule is clockwise, it rotates light in clockwise direction. So then this molecule would be the other side, no, sir?
Of course. Yeah. Remember this. So when you take a molecule, let's say one molecule, and it has enantiomer or the mirror image, and this could be ROS, this could be ROS, and this could be plus or minus, this could be plus or minus, right? So then if this molecule is R and it could be negative, it could be positive as well. Do you understand, Abhishek?
Yes, sir.
So any R molecule or S molecule, they can be, R can be dextrorotatory or levorotatory. That means plus or minus. Even if it is even S enantiomer also can be plus or minus. But as I said, this plus or minus is a property of the molecule, and that molecule can have only one stereo isomerism, right? It could be ROS. So then for each enantiomer, you will assign, let's say for example, you have R isomer and it is positive, right? My point is, you cannot say R has to be positive or R has to be negative. You can't say that. You get what I'm saying?
Yes, thank you.
So if R is positive, then your S has to be negative, because it's the other enantiomer, and these two enantiomers, which we also call optical isomers, they rotate the light in opposite directions. So that is their property. Okay, so right. Okay, so in the question it says optical rotation or alpha D of a mixture of compound F. So now it already says mixture of compound of F. That means it's not a pure compound. So you have both enantiomers in the mixture. So the compound F has maybe two enantiomers, let's say F1 and F2, which are the optical isomers, the enantiomers, these non-superimposable mirror images, and F1 and F2. And so it already says the mixture of compound F and its enantiomer. Yeah, it's a mixture of compound F and its enantiomer. So then that means you have both enantiomers in the mixture. So the optical rotation of that is given as negative 5.1 degrees. That means when you put this mixture in the polarimeter, right? So in here, when you put this mixture of F, it rotates the light in the negative direction, minus 5.1 degrees. That is the meaning. Then the specific rotation of pure F, pure enantiomer, specific rotation of pure F, whatever it is, this is plus 15. So that means let's say you have a compound called you have F and its enantiomer F, let's say F prime, F dash or whatever. So that's the mixture you have. So when you take the pure F, it has specific rotation plus 15. That means if you have only F, it gives you specific rotation plus 15. Okay, question number 1. What is the specific rotation of the enantiomer of F? What is the answer?
Minus 15.
Yeah, very good. See, now we don't know whether it's ROS. It can be ROS. We don't care. So this is something we can measure. So you take the pure enantiomer, you make a solution, you know the concentration, you know the path length, then you measure alpha, then you divide by the concentration and the length, you get the specific rotation. So that when you put F inside, you get plus 15. Then the enantiomer F should be it should have the inverted stereochemistry, or it is the mirror image of the F, and it should be rotating the light in the other direction. So therefore, answer is minus 15. It's very easy. You only have to know the basics. If you know the fundamentals, what is the specific rotation, what is the these plane, what these molecules do to the plane polarized light, and the relationship between the enantiomers, because they always do the opposite. They have the opposite relationship, right? So that's very easy. So it's very straightforward. It's minus 15 because it should be rotating the light in the other direction, the enantiomer. So now then the next question is calculate the enantiomeric excess in the mixture. So we learned these two. There are two equations for the enantiomeric excess or the percent optical purity, because when you have a mixture and it's showing, so when you have a mixture and if the rotation is 0, what does that mean?
The racemic mixture.
Yeah, it's a racemic mixture. That means, yeah, you have the equimolar mixture. You have plus and minus in equal concentrations. But this is not the case. Here it says the mixture has minus 5.1 degrees. That means you actually have the negative isomer in excess, right? So you need to find out how much, by how much. So the optical purity and the enantiomeric excess of a mixture of enantiomers is defined as a comparison between specific rotation of sample and pure enantiomer, and it's given as follows. So you have to get the, it could be defined as the percent optical purity. If you don't know anything about the number of moles you have, you can calculate the optical purity by getting the specific rotation of the sample. The pure sample, it should be divided by the this is the specific rotation of the sample or the mixture divided by the pure enantiomer times 100. Or we can calculate the enantiomeric excess if you know the moles of one enantiomer. I mean, if you know the moles of enantiomers. So moles of one enantiomer, subtract the moles of the other enantiomer, divided by the moles of both enantiomers. You just take the ratio of whatever the specific enantiomer that you're interested in, and you remove the other one, and you get the ratio. So you get enantiomeric excess. Okay, in this case, we don't know the number of moles or anything not given. Only the specific rotations are given, and the optical rotation of the mixture is given. So therefore, we take. So therefore, these both are, when you calculate the enantiomeric excess or the optical purity, this way they're the same. And so enantiomeric excess of this mixture is the optical rotation of the mixture given, and specific rotation of the pure enantiomer also given, pure enantiomer, which is the F. So which is, I had typed it twice. It's okay. The optical rotation of the mixture is minus 5.1. It's given, and divided by minus 15. That is the enantiomer. Sorry, the specific rotation of F. But here's a trick. But they are asking for the enantiomeric excess. We know that the enantiomer in this mixture has a negative rotation. That means we know that we have the negative isome in excess. Do you understand that? Is it clear? Students?
No, sir.
So see, calculate the enantiomeric excess. That means when you have F plus F dash, right? If they're, so these are the two enantiomers, right? If they're if they're equal, if their molar, if their number of moles are equal, if they're in the equal amounts, what you get is a racemic mixture, then the optical rotation is 0. But so imagine this is the plus enantiomer and this is the negative enantiomer. Then if you have them in equimolar, if you have an equimolar mixture, optical rotation is 0. Then when you have a negative rotation, what does that mean? Which one is in excess? Plus one or the negative one?
Negative one.
No, then it is, that's the one in excess. That enantiomer is in excess. So then they're asking you to calculate the enantiomeric excess. So then you have to pick the negative isome. So that's why we put negative 15 in here, not plus 15. Understand? Now, okay?
Yes, sir. Okay, sir.
Right. So then it is 34%. That's the enantiomeric excess. So you have 34% excess of the negative isome. Then the third part of that is find the percentage of each enantiomer in the mixture. So now you have to calculate the percentage of each enantiomer. So the mixture, so we already found out that mixture contains 34% of the negative isomer in excess. That is the enantiomeric excess that we calculated in the part 2. So therefore, so when you have 34% in excess, that's actually caused the minus 5.6, 5.6, was it 5.6? 5.1 rotation, negative rotation. Then so you have to understand that if you had just the minus isomer, you should see minus 15. If you had the plus isomer, you should be seeing plus 15, but actually you're seeing less than that, minus 5.1. And that means you already have, so in here, we have to understand it's a mixture, so you have plus and negative, right? So you have plus and negative isomers both in the mixture, right? And negative one is in excess of 34%. And the other, so if you had 100% negative, you would have seen 15%, sorry, 15 rotation. But the reason that you don't see that, because there's a plus also, there's actually racemic mixture inside. It's not like a racemic mixture inside, but the other 64 or the 66% is actually plus minus, both are in the same quantities. So that's why we see only this one 34%, and it's the rotation due to that 34% excess of the negative isome. So just to get how much of negative isome we have, so it should be 34% excess plus 100 minus 34 divided by 2, that means 66 divided by 2, that is 33. So 33, so then both when you combine those, that's 67% actually negative, and only 33% is the plus isome. So here is the explanation, like only 34%, from the calculation we found out negative isome means in 34% excess. So the rest, that means when you have negative in excess means, so that's the only, it's like that's the only isomer seen by the polarimeter. Oh, that's the only thing causing that rotation of 5.1? Yes, 5.1 rotation. So all the other, the rest, like 100 minus 34, 66% should be racemic. So racemic means that 66% should be plus and negative. And so you divide that by 2. So then 33% of negative and 33% of positive. And then the total negative isomer should be 33 plus the excess 34, and it is 67%. And the rest will be the positive isomer, which is 33%. Okay? Shall we move on to the next one? It's only 2:15.
Okay.
Right. So it says draw the three stable conformations. So this is conformational isomers by rotation of these alkanes. Draw the 3 stable conformations arising from the rotation of the C2 and C3 bond of butane. So this is butane. So we learn about propane and butane. So you can label 1, 2, 3, and 4. So they're asking for the stable conformations arising from the rotation of the C2 and C3 bond. That means this bond. So you have CH3, CH2, CH2, CH3. So they're asking about this bond. So you're rotating this bond. 1, 2, 3, and 4. And these will be substituents. Okay? And identify the chiral and achiral conformations among them. Explain why butane is achiral based on the 3 conformations drawn above. Right. So first you can draw the Sohos models. And so this is, right from the book. So in your notes, you can practice this, drawing. But this is what we need. Okay, Newman projections. So when you take butane, so I'm going to go through this quickly. There are, conformations where I told you, we are considering this bond, right? So the rotation around this bond. So therefore, these 2 CH3 groups, they are like the substituents to that bond. And when these CH3 groups are, staying away from them, as shown in C, I mean, that's the most stable situation because there's no steric interaction. But then you know that when these big groups are eclipsed, as in F, that's the least stable because CH3 groups are eclipsed, and they have the most steric clash, highest steric clash. Then that is the least stable one. So then you have other structures in between them, like D, also unstable because it's interacting with the CH3 and H hydrogen. And these gauge structures like E, G, they are a bit stable than F and D, but they are less stable than C. C is the most stable one. So here also, they are kind of in the proximity. They have some steric clash, but G is more stable than F, right? Because it has less steric clash compared to F. And then you have H as well. So it is similar to the D. It is similar to D. They're the same. Okay. So I mean, those are the 6 conformation you can get from butane. So make sure that you practice drawing these. I mean, it's hard to understand this just looking at the screen. So then you have to draw by yourself. Just turn the. This is right from your notes. Just turn the angles as shown here. 60 degrees and see what happens. It's like I told you. Usually we keep the back carbon. So this CH3 is attached to the back carbon, which is the bigger circle. So this is the back carbon. This is the front carbon. So that means if you label 1, 2, 3, 4. So this carbon is 1. This carbon is 2, and this bigger ring is the carbon number 3, and this is the carbon number 4. Okay, so we usually keep the back carbon intact. So we don't rotate the back carbon. We keep it as it is, and then we rotate the front carbon, which is the carbon number 2. So you rotate the carbon number 2. So 60 degrees means this is 60 degrees. So this CH3 gets here. See, that's what happened here. So when you go to the next next 60, it comes here. See, so then you rotate another 60. This CH3 comes here and it gets eclipsed with the CH3 attached to the back carbon. So likewise, okay. Then if you draw the potential energy variation, I don't think they're asking for the potential energy variation, but you can draw. F is the highest potential one. See because of the eclipse, it has the highest potential. It has the highest energy. That means unstable. And the D and H, I told you they are the same. They are same energy. The same thing. And E and C, E and G, they are they're C is the most stable one. E and G, they are also same energy, and so E and G, they are same, and they are at a lower energy, but the lowest will be C. So, but it make sure that if you have to draw these energy diagrams in a potential energy variation, it's not zero energy. Okay, all these molecules, they have some energy. So it's just a relative energy. That's the important thing. So you just for the comparison, you can show the relative energy. The D, F is the highest, D is the next, and then E, then C is the lowest. C is the lowest doesn't mean C is at zero energy. Right. So then the chirality. So they're asking for draw the three stable conformation arising. Okay. The first question is, they're asking you to draw the three stable conformations. So this is one of them, and E is one of them, and G is one of them. So those are the three stable conformations. See, C, E, G. So those are the three conformations you have to draw as the answer for the first question. Draw the three stable conformations. They're already saying three conformation arising from the rotation of C2C3 of C2C3 bond of butane. Then they're asking, identify the chiral and achiral conformations among them. So we learned that for these alkanes, because of the rotation, you could have chiral centers due to the presence of or absence of center of symmetry. We know that in that most stable conformation E, it is highly symmetric and it has a center of symmetry. So we learned what is the center of symmetry during the day school, right? And so it has a center of symmetry, therefore it is achiral. But the other conformations like D and F, these are the most stable ones. The D and F, they don't have a chiral, they don't have a center of symmetry, therefore they are chiral. The staggered conformations of butane conformers D and F are enantiomers. They are enantiomers, they are chiral, so therefore we call them conformational enantiomorphism. We covered that during the lecture, just to remind you. Right, so therefore now we already identified the chiral and achiral conformations. So this is chiral, achiral. This is achiral because it has a center of symmetry. D and F, they don't have a center of symmetry, therefore they're chiral, and their relationship is they are enantiomers, they are mirror images. The third part is explain why butane is achiral based on the three conformations drawn above. Okay, so the thing is butane overall achiral, but we have only one achiral molecule and there are two chiral molecules. The problem is, they are equal in energy, D and E. See? Sorry.
Excuse me, sir.
Yeah, sure.
So, අපට එතන ප්‍රශ්නේදී කියලා නැහැ sir. So host diagram එකද මේ Newman projection formula එකද අඳින්න ඕනේ කියලා.
Newman projection අඳින්න පුතා ඒක ලේසි. ඒකෙන් ඔයගොල්ලන් ලේසිම explain කරන්න පුළුවන්. මෙතන අර center of symmetry නම් පෙන්වන්න අමාරුයි ඒකෙන්. ඒතකොට center of symmetry පෙන්වන්න ගියාම මේ දෙකම තියනවා නම් තමයි හොඳ. තේරුණාද? නේද?
Yes.
So if you can draw both, that'll be better. Right. So the answer for the third one, explain why butane is achiral based on the three conformations drawn above. So this D and F, they have equal potential energies. So therefore, they will be present in equal concentrations and thus canceling the optical activity. Because I told you, D and F, they are enantiomers, like, RNS or plus and minus. So therefore, their optical activity will be cancelled out. So the one is rotating the light in the clockwise direction, and the other one is in the anti-clockwise direction. So therefore, overall, this butane will be achiral, although these conformations have some chirality, since they are equal in potential energies and they are in equal concentrations. Because if they are equal in potential energies, you will have equal amounts. So it's like a racemic mixture. So it's like these two in a racemic mixture, and so that's why butane is achiral. Overall, butane is achiral. Although you have the chiral conformations, they are in the same amounts or same concentrations because of the same potential energies. Then they actually exist as a racemic mixture. So therefore, it is the overall butane is achiral. Okay, what time is it? Okay, 2:30. So we have time until 3 o'clock, I think. So then Thelma will be taking over. What happened? You can still see my screen, right?
Yes, sir.
Okay. I think I can maybe skip this one because it's it's a very similar one, similar to the one we did before. So I'm going to skip this one so you can try it. It's very similar. And draw chair conformations of the following cyclohexane derivative, giving reason state which chair conformation most stable. So this is a di-substituted cyclohexane. Earlier we did tri-substituted. So first I would is it the same question or what? Okay, so we'll do this one. Okay, so again in a similar question like we did before. So you have trans 1,2 dimethyl cyclohexane and cis 1,2 dimethyl cyclohexane. That means trans 1,2 dimethyl hexane means, so these are like this is actually S trans. S trans means you have usually when we say cis trans, you have carbon-carbon double bonds or alkene. But here we have only carbon-carbon single bond. So therefore, cis or trans, that means if you look at this from this angle, it's like this is going up, and this is the other methyl group is going down. Okay. So therefore, since you have the cis-trans isomerism around a single bond, so that's why it's called S-trans and S-cis, but you don't have to put that in the name. Okay, so you have trans 1,2 dimethyl cyclohexane and cis 1,2 dimethyl cyclohexane, and so then you put this in the two conformations, two chair conformations, and so these are remember that these are two compounds, right? So these are two compounds. Each has two conformations. So this is the two conformation of trans. So you draw the conformation. So as I explained to you earlier, so first you draw the two conformations, then you put the you introduce your substituents. So trans 1,2, that means you have to have a joining substituents in the joining carbons 1 and 2. So 1 CH3. So pay attention to their relative positions. They have to be trans. So this CH3 has to go up and the other has to go down. And when you flip the ring in the other conformation, they still should have the same stereochemistry. And we know that axial become equatorial. and the axial become equatorial. So see now in the flipped ring, they're still there. So this is going up, this is going down actually. So therefore they are still trans. So then how do you, so what would be the more stable conformation? B has to be more stable because A has 1,3 diaxial interaction, as you could see. See 1, 2, 3 position. The hydrogen and methyl will have 1,3 diaxial interaction, but here we don't have that because both CH3s are equatorial. Even this, this one actually A has 1,3 diaxial interaction on the top part and also the bottom. See, this CH3 is interacting with these hydrogens. So therefore, on the bottom side also, it has 1,3 diaxial interaction. Okay, now we go to the cis isomer, cis 1,2 dimethyl cyclohexane, the two rings. So they have to be coming up, because they're cis, they should be, coming towards you if you look at the molecule from above. So, and here axial position CH3 is coming up, and then you have to choose the equatorial one that's also coming up, and that's cis. Then again, to keep the cis, so this equatorial become axial here, okay, and this axial become equatorial, right? So still they are coming towards you, coming up, and they're still cis, but the B conformation and A conformation, they're both the same. They have the both stability because see, both have axial CH3. See, conformation A also has axial CH3. Conformation B also has axial CH3. So they both have 1,3 diaxial interactions the same way. And therefore, these both conformation A and B are equally stable. So they have the equal stability. So you can't say which one is more stable, which one is less stable, but they are having the same interaction, same conformation. So therefore, their stability is equal. Did you understand that? Is it clear enough? Is it okay? Did you understand that?
Yes, sir.
Okay. Yeah, see, yeah, that's the thing, 1,3 diaxial interaction. The same thing, draw in the conformation, okay. So very similar question that like we did before. Right, so I'm going to skip this one as well. So this, I don't remember which year is this from, but it's very similar to what we did before. You want me to do this?
No, sir.
Okay. Then, okay, so now this is some home assignment given to students long time ago, 2019-20. Determine the stereochemical relationship between the two molecules A and B given below. Determine the stereochemical relationship between the two molecules A and B. So you have to determine what kind of relationship they have, okay? Support your answer by giving RNS configurations of the chiral centers of them. Clearly indicate the priorities of groups according to Carney-Wolf-Rieloch rules. So what we need, so it's drawn in a different way, right? So the kind of the bromine in here, bromine there, but you should know, you should be able to see that for each carbon, let's say this is carbon 1 and carbon 2, look at the attached atoms. So this one has hydrogen, this one hydrogen, bromine, sorry, the other one. See, bromine, the carbon attached to bromine, other two groups are hydrogen and CH3. So here also same, right? For the other carbon, where hydroxyl attached to the carbons, its other two groups are CH3 and hydrogen. Understand? So the molecule is just kind of flipped to confuse you. It's drawn in the other way around, like in kind of flipped, right, upside down kind of thing. But you can see that for each carbon, the 2 carbons attached groups are the same. So in this kind of question, what you need to do is you individually find the RNS for both carbons, right? And so when you determine the RNS for A, it's actually turned out to be S and S, because this is 1, 2, 3, and 4. So you hold it away from you. And so it's like you have, see these. So when you hold the least priority group away from you, you can't see it. So this is like, base of a cone. So you take a cone, right? You take a cone. And so here's the least priority group is here. Least, I can't write. My notebook is not working properly, I think. Notepad, actually. This is the least. And then, your other 3 groups are here at the bottom of the cone. I hope you can understand what I'm saying. So then you hold this away from you and you look at the bottom of the cone. Then you see 1, 2, and 3. So that is S, right? So then S, here also S. And then when you determine the other one, compound B, right? Compound A and B, it turned out to be R and R. R and R. So then what you can understand is the A and B are the same, chemically they are same compound, right? So they are chemically same compound because they are the same connectivity, same molecular formula and everything. But then what they're asking is determine the stereochemical relationship. Now you can easily understand, this S center has become R, and this S center has become R. So it's inversion. Each stereocenter inverted to the other kind, or the other, S becomes R, S becomes R. So therefore, their stereochemical relationship is actually, they are enantiomers. They're like mirror images of each other. So then how did we approach this? You take the molecular acids, you find the stereochemistry of each stereogenic center or the stereocenter. Then you can, so then they turn out to be enantiomers. Is it clear? Okay, any questions? Students?
Yes, sir.
Okay. Right, so yeah, but there's one, so this question, we did not talk about the E2 elimination. So I will maybe, discuss about this separately when we, as I said, I will finish that, the remaining 3 sessions very soon. Then I will discuss the E2 elimination part of this question later on, right? So, I mean, that's the only thing different in this question. All the other parts are same as we did before. How to find the most stable conformations, the same thing. You draw the the 2 check conformations and show, attach your substituents and show, so that with the right stereochemistry, and then you can figure out the most stable conformation very easily, as just by considering the less steric clash. And the E2 elimination for that, we'll talk about that later on, as we haven't done that sessions. So it has to have this anti-periplane arrangement for the E2 elimination to occur. So, that's the only thing we need to consider here. So yeah, that's all I have That's all I prepared to discuss on the unit 1. And I think we're almost done. I don't know. Tilma, are you there? Maybe she's not there. So you can ask me any question if you have. We have about